Hi, and I welcome you to this lecture. Here I will be explaining you about Floyd Warshall Algorithm with an example. Now let me just give you an overview of topics I am going to cover in this lecture. To start with, I will be giving you an introduction on Floyd Warshall Algorithm and the kind of problem that can be solved by using this algorithm. Next, I will be explaining you about Floyd Warshall Algorithm with a real-world example. We will deep dive into the algorithm, then we will be implementing the algorithm in Java to solve a problem. Finally, we will be looking into some of the use cases of Floyd Warshall algorithm in real world. It will always be easier to understand an algorithm if we try to learn it by solving a problem. In this case, I'm going to solve a flight path problem by using Floyd Warshall algorithm. Consider a flight that connects 4 cities around the world. New York, New Delhi, Cape Town, and Sydney are the 4 cities that are going to be connected by this flight. There is bi-directional route between Delhi and New York and Cape Town. Notice that rest of the cities doesn't have direct connection between other cities. But you can reach any city by passing through other cities. For example, there is no direct route to New Delhi from Cape Town, but you can reach New Delhi through New York. You can also notice that there are more than one way to reach a city. For example, to reach Cape Town from New York, there are 3 possible routes. There is a direct flight connectivity between New York and Cape Town, or you can reach Cape Town through Sydney or New Delhi. So when a flight starts to Cape Town from New York, the best of these 3 routes should be taken by the flight. To find the best route, a weightage is given to the route between each pair of cities. The weightage is calculated based on number of factors like distance, weather, and air traffic. And this weightage will vary on daily basis. The best route can be picked by choosing the route with lesser weightage. Now the requirement of this problem is we have to pre-compute the best route for each and every pair of cities. Now can we solve this problem using graph? Well, for that we need to check if the data structure of this problem qualifies to be a graph. A graph should have a non-linear data structure, which means the data items should be connected by one or more other data items, and we should be able to traverse through data items. Here in our problem, the data items are the cities. As we can see here, each city is connected by one or more other city, and we can traverse through the cities. So the first requirement is met. The next requirement for a graph is there should be vertices and edges. Here in our examples, cities are the vertices and the connection lines between cities are the edges. So both our requirements are met. So now we are clear that data structure in this problem is a graph. So let's transform this problem into a graph. From now on, for the purpose of simplicity, let's use this graph to solve this problem. Instead of using this complex representation of flight connecting these cities, let's transform this complex representation into a graph. Understand that both these 2 representations are same. I have even named the vertices with acronym of cities in our problem. Similar to this representation, our actual problem statement can also be simplified. So what is the best route here? It's the shortest path. So we can rephrase this as shortest path between every pair of cities. Also, cities are nothing but the vertices. So we can rephrase this problem statement as all pair shortest path between vertices. The most popular algorithm for finding all pair shortest path is Floyd Warshall algorithm. But the only limitation with this algorithm is that we cannot use this algorithm on graphs with negative cycles. We can call a cycle in a graph as negative cycle if the sum of weight in the edges is negative. In our problem, we have 2 cycles. The first cycle is square. As you can see here, sum of weight of edges is not negative. The second cycle is a triangle, and the sum of weight in edges is not negative for the cycle as well. So we are good to use Floyd Warshall algorithm to find all pairs shortest path for this graph. Some vertices in this graph might not have direct path. For example, there is not a direct path for vertex CT to ND, but there is a direct path for the vertices. There is a direct path only for ND to CT, but not from CT to ND. But there is an indirect path from vertex CT to ND. I mean, we can pass through NY to reach the vertex ND. Though there is no direct path, our algorithm should be able to find the indirect path which might go through other vertex. Next, the algorithm should consider all paths between a pair of vertices before deciding the best path. Consider we have to find the shortest path between ND and NY. There are three possible paths to traverse from ND to NY. The first path is direct path and the weightage of the path is 80. The second path to traverse from ND to NY is through CT and the sum of all weightage in the path is 61 plus 3, which is 64. The third path to traverse from ND to NY is through SY and CT. The sum of all weightages in path is 24 plus 20 plus 3, which is 47. Now comparing the weightage of all the three paths, the most cheapest path is third path. And our algorithm should be able to pick exactly the third path as the best path. These two factors I mentioned now are the most important while finding the shortest path between vertices. Floyd Warshall algorithm is the best fit for finding all pair shortest path by implementing these two factors. Now let's see how Floyd Warshall algorithm is deriving the shortest path by implementing the factors I mentioned. Actually, Floyd Warshall algorithm is using dynamic programming approach. For those who don't know about dynamic programming, it's an approach where a large problem is solved by breaking it up into smaller problems. Then the solution will be derived first for the smaller problems. By using the solutions of the smaller problems at different stages, the larger problem will be solved gradually along with smaller problems. In this case, the larger problem is finding the shortest path for all pairs of vertices. What does it mean? We have to find the shortest path between each and every possible pair of vertices. These are the pairs for which we have to find the shortest path. First, let's consider the path from NY. We have to find path from NY to ND, NY to CT, NY to ST, and then finally NY to NY. Yes, of course, there is no sense in considering the path between NY and NY because both are same vertex. Next, we have to find shortest path from ND to other vertices. We have to find shortest path from ND to NY, ND to CT, and ND to SY. And yes, the path doesn't exist for ND to ND because both are same vertex. Similarly, we have to find the shortest path from CT to other vertices and SY to other vertices as I did before. So this is the large single problem we have in hand. How does Floyd Warshall algorithm breaks this into smaller problems? It breaks the large problem of finding shortest path into smaller problem of just finding path between vertices. To start with, the algorithm doesn't care if the path is shortest or not. It will just keep on finding the weightage of direct path and indirect path between vertices. Then by comparing results, Floyd Warshall algorithm will derive the shortest path for each and every pair of vertices. I hope you remember that I already mentioned algorithm should consider both direct and indirect path. In order to deal with these indirect paths for each and every pairs, algorithm will introduce an intermediate vertex to find the indirect paths by summing up the weightage of source to intermediate vertex and from intermediate vertex to destination vertex. Let me show this with an example. To find the shortest path from ND to NY, Floyd Warshall algorithm will first have the weightage of direct path from ND to NY and will have that as a shortest path initially. Then algorithm will substitute other vertices as intermediate vertex between ND to NY. In this case, first CT is substituted as intermediate vertex and now to reach ND to NY, we have to pass through CT. Now the weightage of the indirect path is sum of the weightage of ND to CT and CT to NY. Now Floyd Warshall algorithm will check whether the weightage of this indirect path is lesser than the weightage of the shortest path we already have. If the weightage is lesser, then this path will be saved as shortest path from ND to NY. Next, Floyd Warshall algorithm will substitute SY as intermediate vertex. Now the path will go through SY to reach NY from ND. Once again, the weightage is calculated here by summing the weightage of ND to SY and SY to NY. If the weightage is lesser than the weightage of shortest path we already have, then this path will be considered as shortest path to traverse from ND to NY. Now you might have a question, how I can find the weightage of SY to NY because there is no path. But in this case, we have indirect path from SY to NY, which passes through CT. Floyd Warshall algorithm will compute the weightage of this indirect path between SY to NY, and the weightage will be used while computing the indirect path from ND to NY. This might be overwhelming to you right now, but as the video progresses, you will understand this better with my explanation. For now, just don't worry if you couldn't digest this fully. In any programming language, the input of the program, which computes all pair shortest path using Floyd Warshall algorithm, is passed in as a form of matrix. Let's see how this diagram can be represented as a matrix. Here the column represents the source vertex and the rows represent the destination vertex. Now let's start filling the matrix. Weightage of the path to travel from NY to NY is 0 because source and destination vertex are 0. Weightage of the path to traverse from NY to ND is 33. Similarly, the weightage of the path to traverse from NY to CT is 7. Weightage of the path to traverse from NY to SY is 90. Similarly, I have entered the weightage of path between ND to other vertices. When it comes to distance from CT to ND, there is no path, which means as of now, I cannot reach ND from CT. So we can represent this as infinity because we can never reach the destination. By following this method, I have entered the weightage of other vertices. Well, now this matrix will be the input for the program which computes all pair shortest path. Basically, the program will insert an intermediate vertex in between every pair of source and destination vertex. Let's see this with an example. The program starts its first iteration from the first row, which is NY, and the program will find the path to each of these columns. After completing row 1, the program will move on to row 2, and the shortest path will be found to each of these columns. To show the flow of the program, let's start with row 1, column 1. Here row 1 is NY and column 1 is also NY. I can understand that you are wondering now why we have to find shortest path between NY to NY because both are same vertex. Here I am trying to explain you how the program will iterate through the matrix to find the shortest path by inserting intermediate vertex from NY to SY. So naturally, as a part of iteration or a flow of the program try to find shortest path from NY to NY as well. But in matrix, we already know that NY to NY is 0. So our program will substitute the value 0 and ultimately the shortest path from NY to NY will always remain 0. If you couldn't understand this right now, as the video progresses, you will understand this better when you see the code and when you listen to remaining flow of the program. Now let me continue to walk you through the flow of the program. The next source and destination pair will be NY and ND. Here once again, on inserting an intermediate vertex of NY in between NY and ND, the path will be like NY to NY and from there NY to ND. So we all know that NY to NY is 0 and from NY to ND weightage is 33. On summing 0 plus 33, the result will be 33. It remains same because on inserting NY to NY will be 0. On summing 0, the weightage remains same. So this will be the case for entire first row. When we move to second row, which is ND, so source will be ND and destination will be each and every column from NY till SY. In second row, On first iteration, the source is nd and destination is ny. On inserting an intermediate vertex of ny, the path can be splitted into nd, ny plus ny, ny. Here, the highlighted red color text is the intermediate vertex. nd to ny, the weightage is 80 plus ny to ny, the weightage is 0. On summing, the weightage of nd to ny will be 80. On next iteration in row 2, source will be nd and destination will also be nd. So in this case, on inserting an intermediate vertex ny, the path will be like nd to ny plus ny to nd. The weightage of nd to ny is 80 and the weightage of ny to nd is 33. On summing, the weightage is 133. So now the number has changed. Now we should check whether the path from nd to nd is lesser than 133. Is it lesser? Yes. nd to nd is 0 in this matrix. But on inserting an intermediate vertex, we got 113. Of course, lesser weightage should be given importance. So we will hold the value of 0 for nd to nd in matrix. On next iteration, the source is nd and the destination is ct. On inserting an intermediate vertex ny, indirect path will be nd to ny plus ny to ct. The weightage of nd to ny is 80 plus the weightage of ny to ct is 7. On summing, we get a total weightage of 87. So what is the current weightage we have for nd to ct? Let's check in the matrix. nd to ct, the current weightage is 61. But on inserting ny as intermediate vertex, we are getting a weightage of 87. So we cannot take the new weightage. So the old weightage or the current weightage we have in the matrix will remain there. So similarly, we calculate this for rest of the columns in row 2. On moving to row 3, the first iteration will be ct to ny. On inserting an intermediate vertex of ny, the path will be like ct to ny plus ny to ny. The resulting sum of weightage is 3. Now comes the important point. On next iteration, the source is ct and the destination is nd. On inserting an intermediate vertex of ny, the path will be like ct to ny plus ny to nd. The weightage of ct to ny is 3 plus the weightage of ny to nd is 33, which results in a sum of 36. So now what is the existing weightage for ct to nd in the matrix? The existing weightage is infinity. Now we have to compare this infinity with the resulting weightage we got by inserting an intermediate vertex of ny. The resulting weightage we got is 36. Of course, 36 is lesser than infinity and we have to give importance to lesser weightage. So in our matrix, we will replace infinity with the resulting weightage we got by inserting an intermediate vertex of ny. So this is how it goes on. By following the same method, the program will calculate the resulting weightage by inserting an intermediate vertex. We have seen how programmatically we are going to find the shortest path between each and every pair of source and destination vertex with ny as intermediate vertex. Similarly, our program will also find the shortest path between each and every pair of source and destination vertex by introducing nd as intermediate vertex, and followed by that ct will be introduced as intermediate vertex, and followed by that sy will be introduced as intermediate vertex. So these are the combinations. These are the combination of source and destination vertex with different intermediate vertexes that our program will be using to find the shortest path for each and every pair of source and destination vertex. Currently we have gone through this block. The iteration starts by applying ny as intermediate vertex between each and every pair of source and destination vertex. Followed by that, with same pair of source and destination vertex, we will find weightage by introducing nd as intermediate vertex. Followed by that, we will find the shortest path of each and every pair of source and destination vertex by introducing ct as intermediate vertex. And followed by that, we will find shortest path for each and every pair of source and destination by introducing sy as intermediate vertex. So this is the initial add traffic path that we have seen few slides back, and this is the graph that we derived from this add traffic flow. You might get a question how we can find the shortest path if there is more than one vertex in the indirect path. For example, If you want to find the shortest path from ND to NY, the best indirect path is ND to SY, and from SY to CT, and from CT to NY. Here we have two vertices in the indirect path. You might think of how we will be able to figure out this indirect path which has two intermediate vertices, while our program calculates the shortest path just by introducing one vertex as intermediate vertex. The answer is Floyd Warshall algorithm will effectively deal with this scenario. I hope you can understand that the best path will be derived for this particular use case when Floyd Warshall algorithm introduces SY as intermediate vertex. But even before introducing SY as intermediate vertex, Floyd Warshall algorithm should know the best path to traverse from SY to NY, because the best path from SY to NY will itself have an intermediate vertex, which is CT. So Floyd Warshall algorithm, even before reaching this particular point, it will find the best possible path to reach ND from SY. So that will be calculated here. So here the prerequisite for calculating ND to NY is done even before we reach the point where we calculate the shortest path between ND to NY. Now let me walk you through the Java code for implementation of Floyd Warshall algorithm. Actually, we can implement Floyd Warshall algorithm with just a few lines of Java code. This is the Java code, and in description of this video, I have provided the Git link from where you can get this code. Here, I am creating the input matrix for this program using a two-dimensional array. This matrix is same as the matrix built for the graph in our example. It just has the weight of direct path between all pairs of vertex. This is the method which will implement Floyd Warshall algorithm to derive shortest path for all pairs of vertices. Here we are defining infinity as 999 and total vertex count as 4, which is nothing but the number of rows in our matrix. First, we are declaring a two-dimensional matrix with same size as our input matrix. We will load this matrix with shortest path of all pairs of vertices. Here, in the for loop, we are iterating through each and every rows and columns of our input matrix and copying the values to the matrix we declared to load the output. Then we are iterating through each vertices of our input to fetch an intermediate vertex. With each fetched intermediate vertex, we are iterating through the matrix and summing the weightage of source to intermediate vertex and the weightage of intermediate vertex to destination vertex. If the derived new weightage is lesser than the pre-existing weightage, here we are replacing the new weightage in the output matrix. Finally, after finding shortest path for all pairs, we are printing the output matrix here. Now let's execute this program to see the output. As you can see here, the output matrix with shortest path for all vertices is printed here. Next, let's look into some of the real-world scenarios of Floyd Warshall algorithm. Floyd Warshall algorithm can be used in real-world situations where you have to predetermine or pre-calculate the shortest path for a set of sources and destinations. Now let's see some of the real-world examples where we can use Floyd Warshall algorithm. As I mentioned in my example, Floyd Warshall algorithm can be used in air traffic control, where you can determine the optimal and fastest path of flights. Floyd Warshall algorithm can also be used in applications like Google Maps, where we need to predetermine the shortest path for frequently searched source and destination locations during peak hours, so that you don't have to calculate the shortest path when the user searches for the shortest path from source to destination. This will save the precious time of user. Next, Floyd Warshall algorithm can be used in infrastructures where an object has to be moved from one place to another place based on certain configurable factors. For example, in a data center, storage racks have to be moved from one cabin to another cabin frequently based on the requirements. The optimal route can be derived for all possible source destination cabins at regular interval of time to minimize the time taken at regular interval of time, so that when need arises, we can take the optimal route without wasting time in calculating the optimal route after receiving the movement request. I hope you got a brief understanding about Floyd Warshall algorithm and its real-world use cases. With this, I conclude this video, and if you like my video, just hit the subscribe button and click on notification bell button. Thanks for watching this video.